The music is not in the notes, but in the silence between. When Wolfgang Amadeus Mozart said this, he was really speaking to the very soul of musical composition. Think about it. It's the pauses, the quick breaths, the empty space that actually gives a melody its true meaning and emotional power. Without the silence, music would just be this overwhelming continuous wall of noise. Now, I know that sounds like pure, lofty artistic philosophy, but is actually our absolute perfect entry point into the hard, physical mechanics of sound. Silence isn't just an artistic choice a composer makes, it's a literal physical property that can be mathematically measured, manipulated, and, incredibly, even created by sound itself. Welcome to this explainer where we're going to completely bridge the gap between art and science. We're moving from basic musical intuition straight into the tangible, real-world mechanics of waves, pressure, and energy. I promise you, by the end of this, you will never hear, or I guess not hear, a piece of music the exact same way ever again. Let's get into it. Section 1. The Mechanics of Vibration. Making the invisible visible. Okay, let's dive right into this. To really understand sound, we first have to tackle a pretty massive hurdle. Sound is an entirely invisible force. We hear it constantly, right? But we can't just watch a conversation physically travel across the room. When an object vibrates, let's take a tuning fork, for example, it literally smacks into the surrounding air. And the air isn't pushed cleanly. Instead, it reacts in these tight clusters, bunching up and then spreading far apart in a repeating pattern. This is the visual reality of sound traveling through space. Picture those prongs violently pushing outward. They compress the air molecules directly in front of them, slightly raising the local air pressure. We call that a compression. But then, as they snap back inward, they create a localized vacuum, pulling those molecules apart into a low-pressure zone called a rarefaction. Ultimately, sound is just this outward mechanical pulse of compressions and rarefactions moving outward. Now, what's really interesting here is how we actually calculate this invisible reality. We map these physical compressions and rarefactions directly onto a standard sine wave graph. The high-pressure compressions perfectly align with the wave's peaks, while those low-pressure vacuums drop right into the troughs. Just like that, we've turned invisible air pressure into a clear mathematical curve that we can actually work with. Section 2. The Scale of Loudness, Pushing the Human Limits. So, sound isn't just a shape, it's raw energy. And to measure it accurately, we have to distinguish between two incredibly important concepts. First is intensity, which is the strict, absolute physical measurement of sound energy hitting an area over a given time. And then there's intensity level, which is a really convenient mathematical transformation of that raw physical intensity onto a logarithmic scale so it actually makes sense to our brains. We commonly know this as the decibel scale. And we absolutely need this mathematical transformation because human ears are shockingly sensitive. We can detect pressure fluctuations as incredibly tiny as 3 parts in 10 billion. If we just used raw physical intensity numbers, the math would be completely unmanageable. So we rely on this logarithmic equation to squash that massive, unwieldy energy range down into a neat, tidy scale. To put the scale into a more relatable perspective, let's look at our own biological limits. The absolute faintest sound most humans can possibly detect, the literal threshold of hearing, is pinned right at 0 decibels. On the complete opposite end of the spectrum, the loudest sound we can tolerate before it causes immediate physical harm is the threshold of pain, sitting up at 120 decibels. Basically, every single thing you have ever heard in your entire life lives entirely between these two bounds. But because the decibel scale is logarithmic, it doesn't just work like a standard ruler. So the crucial point is this magic number, 10. It scales exponentially by powers of 10. Here's where it gets wild and where the 10x rule actually has massive business impacts. Multiplying raw physical energy by 10 only adds 10 decibels to the perceived level. Let's think about a real-world scenario. Jet airplanes hit a massive 150 decibels. If an aviation company wants to make a commercial jet cabin just 10 decibels quieter, which is only a moderate perceived drop in loudness for a passenger, they literally have to engineer a way to eliminate 90% of the raw acoustic energy. It's an exponential scale. And that is exactly why commercial soundproofing and industrial noise reduction tech aren't just minor features. They are incredibly complex, multi-billion-dollar engineering challenges. Section 3. When waves collide, the architecture of interference. But what happens when two waves actually collide in the exact same space?
In the real world, waves don't just exist in a vacuum. They share space and physically interact. This interaction is called interference. It's the fascinating process where two or more sound waves from different sources exist at the exact same time, and their energies physically combine, summing together to produce an entirely new single wave.
And this brilliantly illustrates the two totally distinct ways this collision plays out. In constructive interference, the waves perfectly line up. Peaks match with peaks, valleys with valleys, and they combine their energies into a massive, higher-intensity wave. But conversely, in destructive interference, the waves fall entirely out of phase. A peak aligns with a deep valley, essentially causing the waves to physically fight each other. So to summarize, when those compressions and rarefactions line up, they amplify. Boom, a louder sound. But when they're out of phase, they literally swallow each other. This dampening effect isn't just a neat theoretical trick either. It's the exact hard physics powering the active noise-canceling headphones you probably have sitting on your desk right now. It is effectively weaponizing sound to delete sound. Section 4, the architecture of music, bringing it all back to silence. So, we started this explainer with philosophy, mapped the intensity of human hearing, explored massive industrial business challenges, and saw how waves destroy each other. Which brings us right back to destructive interference. Sound waves literally have the physical power to cancel each other out into nothing. So think about this. If Mozart was right, if the true magic of music lives entirely in the silence, and if destructive interference is what actively creates that quiet space, is physics actually composing the ultimate symphony? The next time you put on your favorite song, try listening for the invisible physics of waves canceling each other out. Thanks so much for joining me on this explainer.